Good afternoon, everyone. Let us start. So first, I would like to, again, remind you that our homework 4 is due on this Friday. So if you haven't started, so please start it right now. And again, if you have any questions regarding the implementation, regarding the paper problems, do not hesitate. Just come to the office hour or post a question and issue some discussion on cameras. And then probably at the end of this week or next Monday, we'll release the homework 5, the last homework. And the last homework will mainly focus on neural networks. And probably will include one more model, which is much simpler. It's called logistic regression. So we're gonna, when we finish this artificial neural nets, and we'll briefly introduce another topic called probabilistic learning. That is to use probabilistic framework to formulate learning problems, and we'll introduce two typical learning models. One is called IVS, and the other is called logistic regression. And the logistic regression, the formulation you need to take care of, but the implementation of logistic regression is pretty straightforward. It's just like you implement your least mean square method by replacing the objective with logistic likelihood. So that's our plan. And the second thing I want to remind you is the final course project report. So kick off your good work and start to do that. The final course project report is due on April 27th, if my memory is correct. And it's about like a Friday, and then the next Monday will be our final exam. And if you would like to spend more time preparing the final exam, it's better for you to submit your course project report as early as possible. Right? So again, if you have any problems, you have any issues, just ask. Right? And you can come. So we're going toward the end of the semester. It's less than one month. Right? Okay. Any questions regarding the homework assignments and course project report? Okay, so let us continue with artificial neural nets. So in the last lecture, we introduced the definition of artificial neural nets. Right? So basically, a specific neural network is constructed from a set of building blocks. Right? Each building block, which is considered as a neuron, has the same structure, and basically it connects many inputs, right? And then associated with each edge is a weight, and then going to a neuron, which integrates those information by first doing the linear combination and performing an activation function. So a typical example of a neuron is called linear threshold unit. It is equivalent to a linear classifier. Right? And when we just we just use those as building blocks and connect them together, and layer by layer, you end up with a artificial neural network. And I have introduced the benefit of artificial neural nets mainly in terms of expressing things. Right? Neural network is really called universal function approximator. You can use a neural network to approximate almost all kinds of functions. As long as you increase the layers, you can increase the number of nodes in per layer, you can approximate such kind of function to whatever accuracy you want. That's the benefit for that. And today, we'll continue with neural networks. And we'll first introduce the prediction of neural network, giving you a specific neural network, giving you the architecture, giving you the edge weights, what are the values of those edge weights. What is the specific activation function? Right? And giving you an input vector. How do you compute the output, the prediction? And then we'll introduce the training procedure. So previously, in the last lecture, we mentioned that what is training. training usually assume that you have determined the architecture. How many layers do you have? How many nodes do you have per layer? And what is the activation function? And then the training procedure is to estimate the optimal weights on each edge of the neural network.
I'm just curious, practically, is it totally feasible to build and test on such like a single machine?
Just test on what?
On like a single computer. You know what I mean?
You mean the neural network?
Yes.
No, actually, in most of cases, neural network are trained on single machines. It's not like It's not like training them on like big clusters. Instead, the key to accelerate the training of neural networks are on GPUs. So GPUs is just kind of some kind of card which you can insert them on your board. And usually people won't build up a distributed server to do that. Instead, they want to parallelize the computation in GPUs. And the reason is from the backpropagation. You need to compute. We'll cover what is backpropagation today, right? But you need to compute the gradient layer by layer. That is derivative layer by layer. And there is some kind of parallelization per layer. So we can distribute them into different GPUs. But unfortunately, you must integrate them, you must aggregate them together, go to the next layer. So it's not very appropriate to distribute the computation per layer, to a set of clusters and then aggregate them together. Then there will be much computational communication cost. So you can roughly think of it like training neural net with multiple core CPUs. But unfortunately, those cores are not implemented in CPUs. They're implemented in the GPUs. But the training of modern neural network, basically you can just use mature packages. You don't need to worry about how to compute them, how to distribute computation, how to do parallelization. You don't need to worry them at all. We plan to give a tutorial about how to use TensorFlow to do that. You'll see it's very, very easy. As long as you can give the specification of your artificial neural network architectures and how do you compute the loss function. Then the gradient computation and the parallel computation are automatically finished by the library. That's the benefit. But in your homework 5, you are not allowed to use that to compute the gradient. You need to calculate by yourself. Okay, any questions so far? Okay, so let us continue. So we'll introduce the training procedure of neural nets. That is to estimate the optimal weights on the neural network edges from the data. And the key idea to accelerate the training procedure is called backpropagation. And I will say why it's called backpropagation. So essentially, backpropagation is a way to use the chain rule. And finally, we'll introduce some practical problems when we apply artificial neural nets, and hopefully, when you try to use neural network to solve your problems, you should take into those concerns in your consideration. So first, let us briefly discuss how to predict with a specific neural network. So let us consider an example network here, right? This is just a two-level shallow neural network, and it is a fully connected neural network. If you still have an impression about the definition, so what is fully connected artificial neural network? So each node in current level is connected by all the nodes in the previous level, and also connects to all the nodes in the next layer. It's called fully connected neural network. So basically, there's no missing edges. And then, so here we have one input layer, right, and one inner layer, and one output layer. So actually it's two-layer neural network. As from our naming convention, we do not count the output layer. So we have only two layers, input layer and hidden layer. And we use this X to represent all the input variables. So in this layer, in the input layer, X actually consists of two input variables, X1 and X2. And similarly, we use we use Z to represent the variables in hidden layer. So this Z consists of Z1 and Z2. Right? And also we have an output node Y. But here we have two extra variables in the input layer and hidden layer, X0 and Z0. What's the usage of these two variables? An idea?
Would it be the bias parameters essentially for right or?
Yeah. What's your? Okay. Yeah, you're right. And I'm glad to know that you guys are be aware of this. So the reason we introduce these shaded variables are just to incorporate some bias parameter. It's very similar to like linear regression or linear classifier. So in addition to the feature weights, we want to introduce some bias parameter. And to do so, we introduce these two constant features or constant variables. X0 is 1, Z0 is 1, always 1. So associate the edges connecting Z0 and X0 are the corresponding bias parameter. So you can imagine here is B0 and here is B1, whatever. And so actually we have three input variables in each layer, right? So in the input layer, we have three input variables, X0, X1, X2. So X0 is constant. And in the hidden layer, we have three variables, Z0, Z1, Z2. And Z0 is constant 1. And here we assume that we apply the sigmoid activation function. Meaning that when we do the linear combination to compute the values from the previous layer, then we need to apply this sigmoid function to generate the values for a specific hidden layer node, so Z1 and Z2. So what is sigmoid activation function? Does anyone have any question? Yes. So actually, in neural network literature, it's called sigmoid activation function, but it's also called logistic regression function or logistic function. Whatever, it has many names, but they are all referred to the same thing. So let me write it down. Right? So sigmoid. So suppose S is the input. Sigmoid activation function is defined as 1 minus 1 plus exponential to the minus S. We discussed why this is useful, right? Because a sigmoid function, activation function, is always between 0 and 1. The benefit is that, okay, because each node tries to collect all the information in the bottom layers, right? So if you do not restrict the range of the activation function value, it is possible that your signal or information is just amplified, becomes very, very large. So now if you apply the sigmoid activation function, you transfer them or you squeeze them into a range 0 to 1, so you effectively control the skew of the values. That's the major benefit. So any questions so far? So you know where to apply the sigmoid activation function, right? So if you want to compute Z1, we first do the linear combination of x0, x1, and x2, weighted by the edges, right? And then apply the sigmoid activation function to get z1. And similar procedure applies to z2, right? If you need to compute z2, you need to first do the linear combination of x0, x1, x2, and weighted by the edge weights here. And then you apply the sigmoid activation function as z2. But here there's a little subtle thing, is that in the output layer, we usually do not apply any nonlinear activation function. We just use linear activation function. So what is the linear activation function? It sounds like hyperplane. But linear activation function just means you do nothing. So linear activation function defines as like S. The input S, output is S. You do nothing. So basically, you just do a linear combination of Z0, Z1, and Z2, weighted by the edge weights, 3 edges, right? Then that's it. You don't apply any sigmoid activation function or thresholding function, whatever. That's the convention. That's not the something must be rigorous, but just people who are in the neural network community, you just build up neural network like this. So in hidden layers, in all the hidden layers, they apply the same kind of activation functions layer by layer. But finally, when you integrate all the information to generate output, you do not apply any activation function. Or in other words, you just use linear activation function. You just do a linear combination. That's it.
Do you know why you just not get much from doing another sigmoid activation in the last one? Or?
I think this is just from some tradition. It's not, to me, there's not, a strong reason to keep this. But people just doing things like this. And it doesn't matter. So if you think, okay, I want to apply some nonlinear activation function here, it's okay. You can do it if you like. And but doing this does not increase the flexibility, because I can add one more layer as a linear activation function. So it's totally equivalent to our traditional definition. This is just how people in neural network community do. Any question? Everyone's comfortable? Okay. So now let us look at those edge weights. So suppose those edge weights are given, and here we just want to give some naming convention to differentiate those weights on different edges. So basically, we use both the superscript and the subscripts to denote a specific edge weight. So in the superscript, we denote which type of nodes the edge connects to, or points to. So we can say among those weights, right? So the superscript are either O or H. So just represent, okay, it connects to a node in the output layer or a node in the hidden layer. So we can say, okay, this is a WO01, right? So the superscript is O. You can see the edge connects Y. Y is the node in the output layer. And similarly, you can look at this, right? W22H, Y, the superscript is H because the target node, the ending node, is Z2, right? Z2 belongs to the hidden layer. That's the meaning for the superscript. And in the subscript, we just use two indexes. The index from the index of the node, the edge starts, and then the index of the node, the edge points to. So you can see, let us look at this again, right? This is W001. So the starting node is 0. So say the starting index is 0. And the target index is Y, because there's only one node in output layer. So we, by default, give its index as 1. And W11, oh, this actually, you can see, okay, the starting node, the index of starting node is Z1. So that's the first one where the first one comes from, right? And pointing out to Y, that is the output node. Output node, because there's only one node, so index is by default 1. And you can see, okay, W22 here, right? Starting node X2 and ending node Z2. Okay? Okay, yeah. So, yeah, suppose we are given an input X. And let's see how the output is predicted. Basically, the output, the computation of the output, or in other words, prediction, is from bottom to top, layer by layer. So we compute each node value, and then use those node values as the input, and then compute each node value in the next layer until we reach the top. So we can look at, okay, so we're starting from the input layer, that is the bottom layer, right? We know x0, x1, and x2. So to compute the final output, we need to first compute the intermediate node value, Z1. So Z1 is a linear combination of x0, x1, x2, weighted by the weights on the edges connected to Z1. So you can see this is W01H, right? W11H. So if I express it right now. And this is a W21H. This is a constant figure 1 to account for the bias. So this is 1. And then this is for x1 is weighted by W11H edge right here. And this is x2 and weighted by W21H associated with this edge. So you get linear combination of the input variables. And then you apply the activation function here. And here we use sigma activation function. Of course, we can use other activation function. You get the node value Z1. Right? And similarly, you can compute node value Z2. Use the same process. X0, X1, X2, first linear combination, and weighted by the weights on those edges connected to Z2, right? So it's here. And then, again, apply the sigma activation function to get Z2. And what's the next step? What's the next step? What?
Find Y.
Yeah, find Y. Like how do we get Y?
Basically, apply the same thing that we did for these other ones to Y with the Z's as the inputs.
Yeah. But what's the difference?
The no sigma function.
Yes. Yes. Yeah. That is how you generalize to other nodes. That's generalizability. Okay. So the Y, to compute Y, so you first use all the node values in the previous layer, the hidden layer, right, as the input. And then do a linear combination. And each value is weighted by, again, by the width on the corresponding edges. And here Z0 is 1, constant feature 1. But the difference is that, as we previously mentioned, we don't apply nonlinear activation function at the last layer. So that's why here only on this linear combination. That is, in this procedure, we finished the computation of a prediction given a specific input vector x. This is called a forward pass. Why it's called forward pass? Because we pass the information from the input to output. We call this direction as a forward direction. Okay, any question? Everybody's good? So you don't need some specific example for this, right? You don't need to I give you some values, say 0.5, 0.1, and I show you how to compute that. This is straightforward, right? Okay. So now we finished the prediction step. So giving you any specific artificial neural network, giving you input, you can compute output. Right? It's just pass the computation from bottom to up, from input to output. That's it. Follow the rule. So then the next step is that how can we get the specific neural network? Right? In more detail, how can we estimate the optimal edge weights for neural network? That's our focus today. It's called back propagation. So let us first formulate this training problem. So assume that we are given a network architecture. Namely, we know how do we lay out the neurons. How many neurons, how many nodes in each layer we choose, and how many layers in total we have. And also, we specify the activations. What is activation functions? Do we use the sigma activation functions or Rayleigh activation functions or just the thresholding activation functions? All those things we assume are known before we perform any training procedure. What we do not know are just the edge weights. Right? And then we have collected a data set of labeled examples. Again, they can be represented as pairs of xi and yi. The goal is to learn the weights of the neural network. So the key observation here is that if we have fixed the architecture for a neural network, so the neural network, the output of the neural network, can be simply treated as a function of the input. Right? And the function of the input is only parameterized by the weights W. Right? So although we can graphically show that how we compute the output, right, layer by layer, from this node to the next node, blah, blah, blah. But if you just plug them together into a whole complicated function, it's still a function, right? But just the output of this function is parameterized by all the weights on the edges. That's it. So given x and given w, we can compute the prediction from this function. So now I want to ask, can you come up with some idea to train the neural network? Or in other words, can you come up with some ideas to estimate these parameters for this function? You can try to think about the previous strategy we used to train other machine learning models. An idea? Exactly, right? The same thing as we have done for like this mean square method, right? So what kind of function do we use for prediction in this mean square method? Given you an x, how do you predict y with linear regression? Just a linear function, right? It's just like a W transpose x plus b, right? It's a linear function. But now we use a much more complicated one. That's a neural network, but it's still a function. So now that in training like linear regression, we can come out a loss function over all the training set, and then we minimize the loss function to estimate the optimal weights, right? So why can't we use the same strategy? Just replace the linear regression function by this extremely complicated neural network function. So actually, this is a general starting. You can apply all kinds of prediction model. So we can define a loss, right? And this loss is defined for an entire training set. And each example will have a loss. This loss measures the difference between the ground truth label, the ground truth output, and your prediction. And then you can minimize this whole loss function over the training set to estimate optimal model parameters. So it turns to be an optimization problem. And sometimes people will add some regularizer in front of this loss function. This is called a regularized empirical risk minimization principle. Right? So the last example we mentioned, for the regularized risk minimization is the SVM. And here we can apply the same framework. If you do not apply the regularizer here, this is called empirical risk minimization, because we only have minimized loss over the training data. So far I'm saying this strategy working for a bunch of machine learning models, right? Support vector machines. This is a set of hinge laws. Summation of set of hinge laws over the training examples plus the regularizer. And perception. Perception has their underlying objective function, which is the loss, which resembles the hinge laws. It's still an impression method. And this mean square method. So what's the loss for this mean square method? I heard?
Mean squares?
Yes, just this mean square. You just compute the square of the difference between your prediction and the ground truth, and it just adds up all the squares. That is called, and then we minimize the square summation. It is called least mean square method. Now we apply the same idea for nonlinear models. That is the neural network in our case. So now let us look back to our running example. Right? So this is our simple two-layer artificial neural network, and this is a way how we compute the prediction of our model, right? From bottom to up level. And then suppose the true label for this example is y star, and the prediction is y. And similar to the least mean square method, we can define a square loss as well. It's simply the square of y minus y star, the difference between the ground truth and your prediction, and multiply 1 over 2 just for convenience. So although this looks like very straightforward, I can tell the square loss is the most popular loss function in neural network community. So if you want to show that your neural network is fancy, is good enough, first prove that work in this square loss. And then, given the square loss, right, how do we solve this optimization problem? An idea? Come on, think of it, right? try to use the previous algorithm framework you have learned to generalize this.
Gradient descent?
Yeah, gradient descent. Any supplement? Suppose we have like millions of examples, a billion examples. Stochastic gradient descent. So gradient descent, stochastic gradient descent is like universal tool. Can be applied to all kinds of machine learning models. So whenever you build up your own models and algorithm, you don't need to work out some like very fancy optimization algorithm. Just to try stochastic gradient descent first to see whether it works or not. Then we can use gradient descent. As long as we can compute the gradient of this loss function with respect to the edge weights, we can apply gradient descent or stochastic gradient descent. Obviously, if we are dealing with big data, we prefer stochastic gradient descent. So here, we just plug in our general framework for stochastic gradient descent. When we collect a set of training examples, we initial the parameters W, and W are not necessary to be 0 in training neural networks. And actually, in most cases, we'd better not initialize W to be 0. And then you need to run like big T epochs, right? So each epoch is one pass of the entire training data. You still remember it. And then inside each epoch, we first shuffle the training set at random. And then we go through each training example. Of course, we can go through a batch of training examples as well. And then we treat this specific training example as the entire data set, and then compute the loss over this training example. We call this gradient as the stochastic gradient. Once we get this stochastic gradient, we update the parameters, that is the weights of the neural network edges, by the stochastic gradient descent. So this is stochastic gradient, and this is the learning rate. So when we discuss about stochastic gradient descent for small-back machines, we mentioned that there are many tricks possible for the learning rate. To ensure the convergence of learning rate, it must be square summable, but the summation must be diverged. If you still have some impression, right? But there are many smart schedules for gamma t for this learning rates already. You can directly use them. And here I want to, so this is the same framework. You use it again and again for these mean square methods, simple vector machines, and even perceptron algorithm can be considered as a special case for this, right? But here I want to emphasize that the objective function here is non-convex. It's highly complicated and highly non-convex. So unlike this mean square method, unlike simple vector machines, you cannot assume you finally end up with some global optimal solution. It's not guaranteed. Actually, the solution is severely influenced by the initialization of the parameter study. So the strategy to get an effective initialization is also very important in artificial neural nets. If you look for the literature or look for the if you look at the documentation for the popular artificial neural network libraries like TensorFlow, like PyTorch, you will see there are a bunch of different initialization strategies. And also be aware, don't initialize the parameters W to be 0. In most cases, if you do initialization like this, you end up with very bad local. That's some rules of thumb for artificial neural nets. So it looks like by just plugging in this stochastic gradient descent, we have solved the problem to train a neural network, right? Nothing different here. But there is a major bottleneck. Is the computation of the gradient. As we know, the neural network is expressive in that it has layers of layers, many of nodes connecting to each other, right? So and those weights and the nonlinear activation functions integrate all the information and make a transformation here and here until you reach the endpoint. So the computation of those gradients are usually non-trivial, are really non-trivial. And you can imagine the more the neural networks can be very large. Say, recent paper uses 150-layer neural network to train image classifier. And each layer at least has like 100 or even 500 nodes. And then you can imagine how many parameters you have in total. So the computation is really costly if you just do some naive computation without any tricks. It's not like SVMs or least mean square method, because in general you can consider SVM or least mean square method as a one-layer neural network. So you can apply whatever you feel comfortable. But for deep neural network, for many layer neural network, for very wide neural network, you need to improve the computation efficiency. Otherwise, it won't be practical. And this efficient algorithm is called backpropagation. So before we proceed to the backpropagation, so we end up with we first briefly stop at this checkpoint and see where are we, right? So here's the picture here, right? If we have some specific neural network with structures, activation functions, and weights in hand, we can make prediction for an input. That's what we have discussed so far, right? It's called the forward pass. Right? And then, if we had a true label for the input, then we can define a loss for that example. Based on the forward pass procedure, we can compute the loss. Right? Because we need to compute the output, the prediction, and then you compare the difference between the output and the true input. You can compute the loss. And then, if we can take the derivative of the loss with respect to each of the weights, we can take the gradient step or stochastic gradient step. That's the whole idea. Then the problem is that how can we efficiently calculate the derivative of the loss over each weight? Any questions so far? Everyone is good at this point, right? Okay, so now the key idea in this backpropagation is the chain rule, the fundamental rule in calculus. So I'm pretty much sure you are all familiar with this chain rule, right? So let us do a brief review, right? So what is chain rule? It's a way to compute the derivative for composite functions. So if z is a function of y, and y turns out to be a function of x, then we know that z is a composite function of x. Z is also a function of x. And then how do we find the derivative of z over x? We can apply the chain rule. Chain rule can be graphically represented by this dependency graph, right? So to compute the derivative of z over x, we can first compute the derivative of z over y, and then multiply with the derivative of y over x, right? So graphically, we first compute the derivative of y over x, and then compute the derivative of z over y, and then multiply them together, we get the derivative of z over x. And then we can extend this to like a multiple input function. Right? So suppose z is a function of y1 and y2. So z is f of y1 and y2. And both y1 and y2 are functions of x. Then how do we compute the derivative of z over x? Just do the same thing, but we need to add them together. So first we need to compute the derivative of z is partial derivative. partial derivative of z over y1 multiplying with derivative of y1 over x plus the partial derivative of z over y2 multiplying with partial derivative of y2 over x. So if you write it down as a formula, it's just like this, right? Just as the partial derivative of z over y1 multiplying y1 over x. Enumerate them together. So in general, if we have a z is a function of n variables, so y1, z is function of y1, y2 to yn, and each of these input is also a function of x. And now if we want to compute the derivative of z over x, just do this summation. Right? Summation over all input variables of z, and each segment is partial derivative of z over each input yi, and multiplying with partial derivative of yi over x. So that's the general chain rule, right? Any question? So everyone is familiar with this, right? Okay, so now let us look at how to apply the chain rule to efficiently compute the partial derivatives of our loss function over each of those edges. So this is first, this is a way, this is a loss function, right? Y minus y star is the one-shoot stable. Y is our prediction. To compute the prediction, we need to compute z1 value and z2 values and y, right? And we want to compute right, the partial derivative of loss over all wij o, right? All the o weights and all the h weights. So now let us look at the first one. Let us look at how to compute the partial derivative of loss over W01O. The first attribute connecting Z0 to 1. How can we compute it? So according to the definition, the loss is the half of the square y minus y star. We can apply chain rule. We can first compute the partial derivative of L over y, right? And then compute the partial derivative of y over this attribute, right? W0O. Any question? And then we can say, okay, the first partial derivative is pretty straightforward, right? It's the square loss. So the partial derivative over y is simply y minus y star. And the second one is simply 1. Y. We can look at the output, definition of output, right? So remember the output layer, the node in the output layer is just the linear combination of all the inputs in the previous hidden layer, right? So there's no nonlinear activation function. So this W01O, Z0 is just constant 1, and plus W11O Z1, W21O Z2, right? So if you take the partial derivative of y over W01O, it's simply 1. So now we have finished the computation for the first weight, right? And we can do the same thing for the second weight, W11O, and apply the chain rule again, right? It is equal to partial derivative of L over y and partial derivative of y over W11O. But here, you know, we can find that this partial derivative is computed before, right? So actually, they're shared in the computation of W01, W01O, W11O, W21O. So now that it is computed the first time, we just catch it, just store it. We never need to compute it again. Then when we meet it the second time, we just retrieval the information. And then we only need to compute the partial derivative of y over W11. So what's this partial derivative? Z1, right? So get the second partial derivative. And similarly, we can compute the partial derivative of L over W21 over. And remember, this partial derivative, partial L over partial Y, is already there. We do not need to compute. Just retrieve them and use it. So this is the key observation. So we have already computed this partial derivative for the previous case. So we never need to recompute them. We just catch them to speed up. Now let's look at a more complicated case. What if I want to compute the partial derivative of the loss over this, the second layer, W22H? How can I compute it? We can take a look, right? So first, again, we apply the chain rule. We apply the chain rule. So because L is a function of Y, directly a function of Y, right? So I can first compute the partial derivative of L over Y, and then compute the partial derivative of Y over this W22H here. So again, this one is cached. We do not need to recompute. And then the remaining thing is how to compute this one. And now we need to apply the chain rule again. Because Y is directly a function of Z0, Z1, Z2. And then we use chain rule, we expand it to be partial derivative Y over Z0, and then partial derivative of Z0 over W2H. Right? And partial derivative Y over Z1, partial derivative of Z1 over W2H, and partial derivative Y over Z2, and Z2 over W2H. Right? And now the question is, what's the value of the partial derivative Z0 over W2H and partial derivative of Z1 over W2H? What's the value of this? I heard?
Isn't it 0 because W22H doesn't feed into those essentially, so it has no bearing on them?
Yes. That's a good observation. Yeah. Why? Because you can see W2H only depends on Z2, right? It does not connect to Z1, Z0. So Z1 and Z0 is constant to W2H. So although we use a full chain rule to expand all of them, and actually this term and this term are simply 0. We do not care about these two terms. Then the remaining thing is the partial derivative of Z2 over W2H. So now we can say by applying the chain rule here, the partial derivative of L over W2H is a multiplication of 3 partial derivatives. The first is partial derivative of L over Y, you see, in the upper layer, right? The second is partial derivative Y over Z2 in second layer. And third one is partial derivative Z2 over W2H, the third layer. And remember, because all of other nodes in the second layer, in the hidden layer, is not related to X2, so just threw them out. And now, an important observation here is that, again, this one is computed. Where's computed before, right? When we compute the partial derivative it's not computed, but later we'll say it's computed for other nodes. It's first computed if we first compute W2H. So now let us solve this problem one by one. So first, the first partial derivative is partial derivative of L over Y is Y minus Y star. It's already there. And then the partial derivative of Y over Z2 is W21, right? Because the relationship between Y and Z0, Z1, Z2 is just a linear combination. So you can simply write out the coefficient of Z2 and get the second partial derivative. And then the remaining thing is how to compute the partial derivative of Z2 over W2H. That requires us to know the relationship between Z2 and W2 to H. Then we need to look at the definition. So how can we compute Z2? A linear combination of all the input variables connecting to Z2, right? Weighted by the edges, and then apply activation function here. So the remaining thing is to compute the partial derivative of Z2 over the W2 to H according to this formulation. Again, because if you define this linear combination as some variable s, then the partial derivative of Z2 over W2 to H is this partial derivative of the activation function over s, and then partial derivative of the activation function s over the W2 to H. Right? And the partial derivative of this s over W2 to H is again simply x2. Why? Because this is a linear combination. Then the remaining thing is the partial derivative of this activation function over the input s. That depends on the specific activation function you choose. Different activation functions will correspond to different derivative, right? If you use sigmoid activation function, you have a 1 derivative. But if you use a ReLU function, it's max of 0 and s, you have a different derivative, right? And here you should be aware that for some activation function, it is not a smooth function. It is not a differential. Then what should we do? I heard someone. Yeah, use sub derivative, right? So this is a typical function which is not differentiable, right? Then we can compute the sub derivative. Then the whole gradient, after the whole gradient computation, you end up with a sub gradient. And you can also fit the sub gradient to the stochastic gradient framework. Doesn't matter. So now to give you the concrete example, I want to show you how to compute the partial derivative of this sigmoid activation function over s. So I hope because you should have done it in your own zero. So I hope that won't make you feel complicated. So suppose right now we choose our activation function to be the sigmoid activation function, which is 1 minus 1 plus exponential to the power of minus s, right? So now I want to calculate the derivative over s. So this one is just 1 plus e to the minus s minus 1, right? So we just apply the rule to compute the derivative. It's just straightforward. So we put minus 1 in front. So we have a 1 plus e to the minus 1, and the power should be minus 2. And then you apply the derivative for this term. So it's simply e to the minus s. And again, you need to apply the rule again, right? It's a minus 1. So 2 negative becomes 1 positive. So end up with 1 plus 1 over 1 plus e to the minus s squared. This is this term. And this term, and the x term is e to the minus s. And now let us look at make just a simple manipulation of this term. So end up with a very beautiful conclusion. So because it's just a square of this 1 plus e to the minus s, right? Let's just write it down as a production of the same term. So it is 1 plus 1 over 1 plus e to the minus x times 1 over 1 plus e to the minus s, then times e to the minus s. So what's this term? What's this term? Yeah. We get back to our sigma activation function. So the first term is simply the sigma activation function. And what about this term? Any observation? So this one is simply 1 minus a sigma activation function, right? So if you just subtract 1 by this sigma activation function, what can you see? It's this, right? Because you have the numerator will have an extra term e to the minus s, right? You subtract it by 1, you end up with this. You end up with this. So this is a famous conclusion. I hope you guys can have a kind of impression. So the partial derivative of the sigma activation function is simply the sigma activation function itself multiplying with the sigma activation function 1 minus the sigma activation function. Any questions so far? Okay, so just some trick observation in computation. So now let us continue, right? So we have knowing that this partial derivative of sigma activation function is simply this product, right? And also we know the actual we know this partial derivative of s over w2h is simply x2. We just combine them together, we get our partial derivative of z2 over w2h, which is this. And now we have 3 derivatives in hand. The first one, partial derivative of L over y, here. Second, partial derivative of y over z2. This is straightforward because y is a linear function of z2. Y is a linear combination of z0, z1, z2. Directly read it out. And finally, the partial derivative of z2 over w2 to h. You apply the chain rule again, you get this. And then you multiply them together. You end up with our partial derivative of L over the w2h. So now we can say first, y minus y star is catched, right? And second, this w20, although it's first computed, but next time we will compute the partial derivative of L over this term, or this edge. They can be shared as well. So similarly, we will compute partial derivative of what actually here. They can be shared as well. So you can see, as we proceed layer by layer, from top to bottom, when we compute derivatives, we can catch all the partial derivatives we have computed so far, because they are going to use them. They're going to be used in the next layer's derivative computation. That's the key idea. So let's look at it again, right? To compute the partial derivative of L over W2 to H, it depends on the variables Y and Z2, right? Those yellow shaded one. And then you get the partial derivatives along the path here. partial derivative L over y, and partial derivative y over z2, and partial derivative z2 over x2. And during the computation, the partial derivative here and partial derivative here are all cached. So every time when you compute, you just use those cached values. You can save a lot of computation. This is just for the 2-layer case. In the most general case, if you want to compute the partial derivative of the loss function for arbitrary h, say wh, from node m to the node n, and it requires you first draw all the path from the target node n to the root node y. And then your computation only relates to the partial derivative over nodes on this path. So here we say, okay, the partial derivative for W2 to H, right? So the target node is Z2. So we draw the dependent partial derivatives are on the path from Z2 to the Y. So we can say, oh, there are only 2 nodes here, right? So in your computation, it requires the partial derivative on these 2 nodes. That's called a dependency graph. So if we can now let me show you a more general case. So in a more general case, suppose you want to compute the partial derivative for edge weight in the 3rd layer. So this is a edge weight we're interested in, right? And now we know, okay, this edge connects to this node, right? And to say what kind of partial derivatives it relates and depends on, we just draw all the paths from this node to the root node 1. This is the output. And then it is very probably that there are multiple paths. So you should be aware of this. It could be like this. And also connect to this. And now we say, okay, the path which connect to the y and the target node here, consider those nodes, right? And then we can denote this node by, say, W O, or just random write it like W12 or 1, 2, 1. One, and this node we can say written as WH N4, whatever. And then your computation, you can say, okay, all the paths which connects from Y to the target node here, and your computation will be partial L or partial Y, right? First node, and then partial Y over partial WO31, this node, plus partial Y over partial WO21, this node. And then the last layer. So it's now the Z3 and Z2, and this is Z4. So So you can see a node Z3, Z2, and Z4 in the past, right? So you need to compute a partial derivative of L over Y, that's for sure, and multiply with partial derivative of L over Z3. And plus partial derivative of L over Z2. And then, Z3 and partial derivative of Z3 over Z4 plus partial derivative of L over Z2, partial derivative of Z2 over Z4, and then partial derivative of Z4 over W N4H. Is it clear? So let me repeat again. I'm sorry for this massive graph. So suppose this is some node, right? We can write it as Z4, right? And there is some edge here, and this is WN4H. And this is our Y node. This is output. I want to compute the partial derivative of the loss function over WH4. To compute this, we need to find the dependent partial derivatives. So how to find it? We draw a path from the target node Z4, that is the edge connector, and draw the path from Z4 to the Y. There could be multiple paths. So it could be one node here, right? So we can draw it as a Z1 and Z2. And then they are all connected by A3. And this 3 is connected by Z4. So we can say, okay, there are two passes. And it requires all the derivatives on these passes. So if you compute it, it will be like this. So first, you compute the partial derivatives on the first node on this path, which is partial derivative of L or partial derivative Y. And second, we just enumerate each path. Partial derivative Y over Z1. And then partial derivative Z1 over Z2. Partial derivative Z1 over Z3, right? And then partial derivative Z3 over Z4. And finally, partial derivative Z4 over the weight. This is one path. That's just the one path. Right? And then we go through another path. This path. So the first is partial derivative of L over Y, we have computed here, right? So it's on the outside. And second is from here to here. So it's partial derivative of Y over Z2. Right here. And then partial derivative of Z2 over Z3. Right here. And then partial derivative of Z3 or Z4 right here. And finally, the partial derivative Z4 over the weight. Right? And of course, because there are some sharing parts in this two path, right, you can just take out the common terms. But this is the way how we compute the partial derivative for this specific athlete. And when we compute those partial derivatives from top to the bottom, all those partial derivatives are pre-computed, right? So when we use them, we just retrieve them. And what we only need to compute is this one, partial derivative Z4 over the Wn4H. That's it. And in the previous partial derivatives, we just read out from the previous notation. And because this direction is from the top to the bottom, from the output to the input. So it's called back propagation. Because the forward pass is from input to output. Now we reverse it from the output to the input to propagate all those partial derivatives. So it's called back propagation. So what is propagate? It's just the partial derivatives. Okay, so that's the key ideas for the back propagation. And on Wednesday, we'll give a general framework for the back propagation and give you a more detailed example to compute, to use back propagation to compute the gradient. And we'll see you on Wednesday. Okay. Yeah, it's arbitrary, but you better use that. Like you can have two, say, you can use cross, right? Just frequency, but you can even manually check or some probably better. Yes, yes, doesn't matter. Of course, the best way is yeah, just the D here. Oh yeah, the same as loss function. C is the same as.
That's how I have it.
Okay. One class? Yeah. Oh, okay. So